What's up, everybody? Mr. Cozad back again for another video lesson. Today's topic is on graphing rational functions. Okay, this gets interesting. Graphing rational functions is fun. It's exciting because every little function that you see is going to be a little uniquely different than the previous. So if you have not watched the 8.3 video on graphing reciprocal functions, I would suggest going and checking that out first. I'll put the link in the description of this video. Go watch that first because it goes through some of the background and basics of these graphs that I might go through more quickly in this lesson. So it might be a good idea for you to watch that one to get a good idea of kind of what the shapes of these graphs looks like and some of the background information. Okay, if you are my student, this is from 8.4 in our textbook, and this is part 1 of a 2-part series. Okay, so come back and check out part 2 with some even more interesting graphs and types of functions. So before we go on any further, I got to tell you, today's a great day to be alive. Wherever you are, whatever you're doing, remember that. Today's a great day to be alive. So for this lesson, all that you need is something to write with and something to write on. If you got those two things, man, let's get after it. Here we go. So, general rational functions. Okay, this is what I was talking about a little bit a minute ago. There are infinite possibilities here. Anything in the form f of x equals a polynomial over a polynomial. That opens the door to tons and tons and tons of different scenarios, different looks, different types of equations. What I did here is I just came up with 4 pretty simple different types of functions where you've got a different type of polynomial on the top and a different type of polynomial on the bottom. We're not going to solve these right now. We're not going to do anything. This is just for you to look at. This is just 4 of many different examples that you could see that are considered general rational functions. Okay, remember the last lesson with reciprocal functions was very, very specific, the form that we were looking at. But these ones, it's kind of like the Wild West. There's lots of different combinations of things that can happen. You can have something crazy on the top, something crazy on the bottom, all different types of functions, combinations of things, so long as it's any polynomial on the top divided by any polynomial on the bottom. Okay, so you're going to be asked to graph these rational functions and identify some key attributes. So this lesson, what we're going to do is we're going to go through a series of, I think it's 5 steps that you can always approach on tackling these problems. Okay, so step 1 is to find the vertical asymptote. Okay, now if you watched the last lesson, you know the vertical asymptote is the x value that makes the denominator equal to 0. And in this case, sometimes there will be more than one vertical asymptote. So the way that we identify our vertical asymptote, remember we're going to abbreviate it as VA. Okay, and hold on, I want to change this. Let's do purple. Yeah, okay, so the vertical asymptote, the way that you're always going to find the vertical asymptote is set denominator equal to 0. So 0 equals x squared plus 2x minus 3. Now, this is a quadratic that can be factored, and we'll do that. X plus 3 times x minus 1. And then we set each of those equal to 0 and solve. We get x equals negative 3, and we get x equals 1. So in this particular problem, there would be 2 vertical asymptotes. There'd be a vertical asymptote at x equals negative 3, and there'd also be a vertical asymptote at x equals 1, okay? In general rational functions, we can have more than one vertical asymptote. It's however many x values make your denominator equal 0. So, again, to find the vertical asymptote, set your denominator equal to 0, and it's okay if you get more than one, okay? So that's step 1. Now, step 2 is the step that is, in my opinion, the most complicated in these general rational functions like this, okay? So it's to find the horizontal asymptote, okay? And the nice thing about the horizontal asymptote is there will be at most one. You will not have 2 or more. You'll have at most 1. Sometimes you won't have 1 at all, okay? So here is kind of the strategy that we're going to use to help us identify this. We're going to use 3 acronyms: BOBO, BOTN, EATS DC. Sounds really silly, but I promise you that students in the past have told me this is a really, really useful tool and helping them identify the horizontal asymptote. Okay, so here's the question that you're going to ask yourself, okay? And the answer to this question tells you which of these acronyms you're going to use. So if the degree, write this down, if the degree is BOBO, here's what BOBO stands for. Bigger on bottom, bigger on bottom. That's what the BOB stands for. So if the degree is bigger on bottom, then your horizontal asymptote is 0. The horizontal asymptote is 0. So bigger on bottom, 0. BOBO, bigger on bottom, 0 is what you would remember. So if the degree is bigger on the bottom, that means that the greatest exponent you see in the denominator is larger than the greatest exponent you see in the numerator. That's a scenario where the degree on the bottom is bigger on bottom than on top. Then your horizontal asymptote is y equals 0. It doesn't matter what the numbers are. It doesn't matter anything. If you see it's bigger on bottom, then 0. Then y equals 0. Okay? Now the next one, a bottom. Okay, so remember the same question we're asking every time. If the degree is, bottom is bigger on top. So if the degree is larger on the top than it is on the bottom, then the horizontal asymptote doesn't exist. There isn't one. Bigger on top, none is what that acronym stands for. Bigger on top, none. So if the degree is bigger on top, then the horizontal asymptote is none. It's non-existent. It doesn't exist. Okay? And the third and final one, okay, eats DC. So if the degree is, wrong word, exponents. So exponents are the same. That means the exponent on the top matches the exponent that's on the bottom. It's like x cubed on the top and x cubed in the denominator, okay? So then what you do is then the horizontal asymptote, you divide the coefficients. You divide the lead coefficients. So if the exponents are the same, divide the coefficients. Eats DC. Watch it again. Watch the letters as I read it. Exponents are the same. Divide coefficients. Okay? So the next page, I'm going to show you some different scenarios where we identify whether it's a BOBO, a bottom, or an eats DC, and then we use these rules to find the horizontal asymptote. Okay? So here we go. Bear with me. The light bulb's going to turn on once you see it in action. Okay? So for examples 2, 3, and 4, it says find the horizontal asymptote for each. Okay, step number 1. Okay, step number 1 is we want to identify whether this is a BOBO, a bottom, or an eats DC. Okay, so look at example 2. The degree on the top is a 2. The degree on the bottom is also a 2. So which of the 3 scenarios is this? Is this a BOBO? Is it a bottom? Or is it an eats DC? Okay. Probably feels ridiculous to say that out loud, but somebody probably said it out loud. I'm talking in a room by myself. It's cool. So when I ask you questions, it's okay to just say the answer like you would in class. It's not weird, I promise. It's probably a little weird, but that's okay. Weird is normal and weird is cool, okay? So this is an eats DC. So when it eats DC, exponents are the same. Divide the coefficients. So we know that a horizontal asymptote will always be y equals. The lead coefficient on the top is a 3. The lead coefficient on the bottom is a 6. So this horizontal asymptote would be at y equals 1/2. That's how we find our horizontal asymptote. Okay, moving on to example 3. Okay, the degree on the top is 0. The degree on the bottom is 2. So this is a bigger on bottom. So this is a BOBO, which means our horizontal asymptote, if the degree is bigger on bottom, y equals 0. Remember, this has nothing to do, none of the other numbers in this function matter at all. If the degree is bigger on the bottom, you automatically default to y equals 0 for the horizontal asymptote. And example 4, okay, we've got an x to the 4th on the top, and we have an x squared on the bottom. So this is a bigger on top. This is a botan. So when we have a botan, the horizontal asymptote does not exist. We'd say there is none. Okay? All right, so we found the vertical asymptotes. Remember back to that, vertical asymptotes. We set the denominator equal to 0 and solve for x. For the horizontal asymptotes, we use these acronyms, BOBO, botan, EATS, DC, to help us figure out the horizontal asymptotes. Okay? All right, step 3 is to find the x-intercept or x-intercepts, plural. There could be more than one. So to do that, we are going to set y equal to 0 and then solve for x. It's the same way you've been finding x-intercepts all the way through algebra and geometry in this class so far. So find the x-intercept for each of these functions. All right, so we're going to set the function equal to 0. Okay, so we get 0 equals x squared minus 4 all over 2x minus 1. Now, if you multiply both sides by 2x minus 1, we get 0 times 2x minus 1 equals x squared minus 4. Conveniently, 0 times 2x minus 1, 0 times anything just becomes 0. So we get 0 equals x squared minus 4. Now listen very, very carefully to what I'm about to say. This is a kind of like a cheat code. You can, if your function is one fraction, meaning one numerator, one denominator, nothing over here, the way you can find the x-intercepts is you can take the numerator and simply set the numerator equal to 0. Again, listen very carefully. If it's one fraction, meaning nothing plus or minus out here, okay, if it's just one fraction, one numerator, one denominator, you can skip straight to this step and set the numerator equal to 0 because it'll always work out that way. Okay, so x squared minus 4 is a difference of squares, so we get x plus 2 times x minus 2. So we get two x values. We get x equals positive 2 and x equals negative 2. And then because these are x-intercepts and we want to write them as the coordinate of points, remember to write them out as negative 2, 0, and 2, 0 are my x-intercepts. Okay? Now, I specifically wrote example 6 the way that I did to show you that in this particular scenario, you don't have just one fraction. You've got a fraction here, and you've got a whole number here. So you can't just set the numerator equal to 0 in this case. Okay? So what we're going to do is we're going to set this equal to 0, and we actually have to solve this one out. So subtract the 3 on both sides. You get negative 3 equals 2 times x minus 5. Multiply both sides by x minus 5. So you get negative 3x plus 15 equals 2. Then we subtract 15 on both sides, so we get negative 13. So we get that x equals positive 13 over 3 after I divide by that negative 3. Now, last thing that I want you to do is the x-intercept is an actual tangible point, a real point on the graph. So that means we write it as the coordinate of a point, 13 thirds, comma 0. So that is step 3. Step 1, identify your vertical asymptote. Set your denominators equal to 0. Step 2, find the horizontal asymptote. Use the acronyms BOBO, botan, EATS, DC. Step 3, find the x-intercept. Okay. Step 4 is to find the y-intercept. Now, there can be at most one. Okay. This isn't going to be a scenario where there's multiple possible y-intercepts like there were for the x-intercepts. Okay. So this is actually pretty straightforward algebra here. We're going to set all x values equal to 0 and then solve for y. Okay, so for example 7, we're going to basically solve f of 0. So that means we plug a 0 in for every x that you see and simplify. So we end up getting negative 4 over negative 1, which equals positive 4. So our y-intercept here is 0, 4. Most of the time, the algebra and finding the y-intercept turns out to be really easy. Okay, it turns out to be really easy. Okay, same deal here. We're going to take f of 0 on example 8, and we're going to plug a 0 in for every x that you see. Some of you might actually be able to find these mentally, because plugging a 0 in might be easy mental math for you to do. Others of you, you might need to actually write it out. It's no big deal, okay? So 2 over negative 5 is negative 2/5. Plus, instead of plus 3, I'm going to do 15/5, which is the equivalent of 3. But that allows me to pretty quickly combine those into 13/5. So again, write that as a coordinate 0, 13/5. So finding the y-intercept, I think, is pretty easy. All you do is plug x in, or plug 0 in for x, and solve for y. So step 1, find the vertical asymptote. Set the denominator equal to 0. That's how you do that. Step 2 is to find the horizontal asymptotes. You use your acronym, Bobo, Botten, Eats, DC. Okay. Step 3 was to find the x-intercepts. If it's one fraction, one numerator, one denominator, you can set the numerator equal to 0 to do that. If it's not, if it's a scenario like this one was, you have to plug a 0 in for y and solve for x. And then step 4, the one we just did, plug a 0 in for every x you see and solve for y. Okay? So step 5 is to sketch a graph of the function, start with the asymptotes and intercepts, and make a table if you need more points. So here's what we're going to do. We're going to put everything together that we've already done, all 4 steps in one context here. Okay, so here we go. Step 1, I've repeated it every page along the way, but step 1 is to find the vertical asymptote. So how do you find the vertical asymptote? Hopefully you said set the denominator equal to 0. So when we set this denominator x plus 3 equal to 0, we can do that mentally and we get x equals negative 3. That is the location of my my vertical asymptote. So I'm going to go to my graph and I'm going to put a asymptote at negative 3. Okay. Next, we're going to find our horizontal asymptote. Now, this is the one where we have to use those acronyms, Bobo, Botten, Eats, DC. So if you look at this, which of the 3 scenarios is represented here in this function? Okay, this is an Eats DC. So that means the exponents are the same. So to find the horizontal asymptote, we divide the coefficients. 1 divided by 1 is 1. So my horizontal asymptote is at y equals 1. Okay, I've got my asymptotes. Now the next thing that I'm going to want to do is find my x-intercept. Now for my x-intercept, okay, remember, what we can do is we can set the numerator equal to 0 and solve. So when I do that, x minus 4 equals 0, I get x equals 4, and I'm going to write that as the coordinate of a point. Okay, so that's the point 4, 0. So I'm going to add that to my graph. 1, 2, 3, 4. Put that right there. Okay. So what that tells me, guys, is the location of that point tells me there's going to be a branch that's somewhere in this quadrant right here. And there's going to be another one up here somewhere. Okay, so that's a good piece of information that we just gathered here. Okay. Now the next thing we'll do is find the y-intercept. Now the y-intercept, you plug every x you see equal to 0. So we get negative 4 over 3. Write that as a coordinate of a point. That's 0, negative 4/3. So that's another point that we can graph. When x is 0, y is negative 4/3, which is down here. Okay. So with those 2 points, I actually feel pretty comfortable drawing a sketch of that line or that branch. Remember from the last lesson that these asymptotes function like magnets. They draw the ends to themselves. Okay, these ends of these branches are magnetically drawn to the asymptotes. And remember, they get really, really close, but they do not touch. Okay, now what we have to do next is we have to find the location of the branch that's going to be up here. And the only way to do that, and to do it well, is to make a table of values. So we'll just pick a few points. Specifically, we're looking at x values in this area right here. So let's try negative 4. And let's do negative 6. So what I'd like you to do, I'd like you to try to plug negative 4 in for x and then negative 6 in for x and see what you get for y. Okay, so when I plug negative 4 in for x, you should have had 8. And when you plug negative 6 in for x, you should have gotten 10/3. Okay, so let's plot those 2 points as well. So negative 1, 2, 3, 4, and 8 is way up here at the top. And then -6, 10/3, 3/3, 6/3, 9/3, just a little bit above 9/3. Looks like this. So that is, don't have as much room on this graph to draw that, okay? But it would be a branch that looks something like this, okay? Guys, that's the basics on, basics 5 steps on graphing any rational function. Step 1, to recap, find the vertical asymptote by setting the denominator equal to 0. Step 2, find the horizontal asymptote. That's where we use that acronym Bobo Botten eats DC. Step 3, find the x-intercepts. Make y equal to 0 and set the numerator equal to 0. Solve for x. Step 4 is to find the y-intercept. Make every x equal to 0 and solve for y. And then step 5, put it all together on a graph and you create a table if you need to find some more points to be able to draw accurate branches of this graph. Okay, that's it for part 1. Come back for part 2, where we will continue to look at some more interesting aspects of rational functions. See you next time.